myself Swaran Singh, lecturer civil engineering from Pandit J.R. Government Polytechnic College, Hoshiarpur. Today our topic is soil classification and identification. The definition and purpose of the soil classification. Soil classification is the method of arranging soils into different groups such that the soil in a particular group have similar behavior. The purpose of soil classification is to classification, systematize or classify the soil into branch groups according to their engineering or other characteristics. It is always more convenient to study the behavior of the groups than that of individual soils. When the soil consists various constituents in different proportions, the mixture is given the name of constituents that appear to have significant influence on its behavior, and the other constituents are indicated by adjectives. Importance of soil classification system. A soil classification system serves the purpose of exchange of information and experience between the soil engineer. In other words, it is a connecting link between engineers dealing with the soil. A soil classification system which uses easy and simple method of identification and gives an approximate but fairly accurate system of separation into soil groups. The soil in nature rarely exists separately as gravel, sand, silt, clay or organic matters, but are equally found as mixtures with varying proportion of these components. Next, basic requirements of soil classification system. It should be based on some scientific method. Number 2, it should be simple and easily understood. Number 3, it should have limited numbers of groups. Number 4, it should be based on few simple tests which can be easily performed in the laboratories. Number 5, as it is a connecting link, it should be acceptable to all civil engineers dealing with the soils. Number 6, it should be based on the specific engineering properties which are most relevant for the purpose for which the classification system has been devised. Number 7, it should be fairly accurate system through it give results. Next is index properties. So, the properties of the soils which are not very important for soil engineer, but give some information about the main engineering properties like permeability, compressibility and shear strength required for the design of important structures are known as index properties. Next is particle size and shape. The size of soil particle range from gravel to the finest possible clay size. Their characteristics also vary with the size. The soil particle coarser than 75 microns या 0.075 mm are visible to the naked eye and can be examined by hand lens. Soil particle finer than 75 microns are not visible to the naked eye and can be observed only under a microscope. However, shape of particles smaller than 1 micron is equal to 0.001 mm, means 1 mm is equal to 1000 microns. Size can be determined only by means of electron microscope. So, this is the var chart diagram that show according to the size of the particles and their groups, particle size and shape. From the bottom, that is boulder, gravel. Gravel is also first groups that is known as boulder, 300 mm and above size, 300 to 75 mm tak, that is known as cobble, 75 to 4.75 mm tak, that is the gravel. Coarser fraction, that is the three type: coarse gravel, fine gravel and medium gravel, coarse and fine. Next is 4.75 mm to लेके 75 माइक्रोन तक या 0.075 mm तक, that is shown the sand. That is also the in the three groups: coarser sand, medium sand ਤੇ fine sand. 0.075 mm to the bottom side, that is the silt, up to the 0.02 mm ਤੋਂ ਵੀ ਥੱਲੇ ਬਹੁਤ fine particles ਜਿਹੜੇ, that is known as clay particles. So, these are the var group chart that shown the. So, the coarser fraction of soil consists of gravel and sand. Gravel and boulders, cobble, that are larger size than the coarser fraction. So, the coarser fraction, that is the gravel from 75 mm to 4.75 mm. That is the two type: coarser and fine. Next is sand particle. Sand particle three type. So, the individual grains of gravel and sand may be angular, subangular, sub-rounded or well-rounded as shown in next table. So, silt and clay constitute the finer fraction of the soil. The soil particles may be angular, flaky, or sometimes needle shaped. So, the shape of the particles that is shown in this table as number 1 angular shape. These are the shape of the particle in this type of the particle in shape. Number 2 subangular, number 3 sub-rounded, number 4 rounded shapes particle, number 5 well rounded, and number 6 flaky shape particles of the soils. So, these are the many types of the shape of the particles: angular, subangular, sub-rounded, rounded, well rounded and flaky type shapes. Particle size and shape: soil particles coarser than 0.075 mm are generally termed as cohesion less, and particle finer than the size 0.075 mm are known as cohesive soil. So, there are two types of the soil: the larger particle size, that is the cohesionless soil, and finer than 0.075 mm, that type of soil is known as cohesive soils. So, from the engineering point of view, these two types of soils have distinctive characteristics. In case of cohesionless soils, gravitational forces predominate and are responsible for their engineering behavior, whereas interparticle forces are predominant in case of cohesive soil. Number 1, the shape of the particles is responsible for reduction in the volume of the soil mass upon the application of the pressure or load or stress to the soil sample. Second, addition of small mixtures of mica to sand result in large increase in its compressibility. So, when we added the small percentage of mixture of the mica to the sand, that is the cohesionless soil, larger particle result in large increase in its compressibility. Clay minerals: the soil particles finer than 2 micron size 0.002 mm, that is also known as 2 micron size, are referred to as a clay particles. The word clay indicates a material soil mass composed of a small mineral particle which exhibit the property of the plasticity in association with certain quantities of the water. When we add or mix the water into this soil, then they give the property of the plasticity. So, these small crystalline minerals particles are essentially hydrous aluminum silicates and are commonly known as clay minerals. Clay mineral can also contain organic matter and water soluble salt. The important clay minerals are kaolinite, example as China clay, montmorillonite as black cotton soil, elite example as shale type soil. So, these are the three important clay minerals: kaolinite, montmorillonite, illite, present in the clay particles of the soils, which provide the plasticity to the soil when associated with certain amount of the water. Clay minerals, the basic structural unit of these clay minerals consist of an alumina sheet, that is represented by G, or gibbsite, combined with silica sheet, that is represented by S. The thickness of these structural units is measured in terms of angstrom A, that is 1 angstrom is equal to 10 the power minus 7 mm. In case of kaolinite, the structural units rejoined together by strong hydrogen bond, where as in case of illite, it is shown in this figure. In the first figure, kaolinite minerals, these are the alumina and silica sheets. Total bond in between two sheets, that is the 7 angstrom, and between the two plates, the bond formation in between these two segment, that is the hydrogen bond in the kaolinite minerals. So, in case of kaolinite, the structural unit rejoined together by strong hydrogen bond, whereas in case of illite by non-exchangeable potassium ions. But in case montmorillonite, two successive structural units are only linked between oxygen ions of two silica sheets. It is the reason the soil containing large amount of montmorillonite minerals show high shrinkage and swelling characteristics. So, these are the figures shown the bond in between the two sheets and kaolinite minerals, that is composed of the silica and alumina sheets. These two segments are joined together by the hydrogen bonds in between the two segments. The total thickness of these segments 7 angstrom and 7 angstrom. So, in montmorillonite minerals that have contained the one segment that is composed of the silica, alumina, silica sheets. The total thickness of these one segment is 10 angstrom, and same as the other segment, that is also the 10 angstrom thickness, and same the sheets composed of the silica, alumina, silica. So, these two segments that are composed, associate, joined together with the water molecules that are present in between the two segments. So, that total structure of this type of mineral is the montmorillonite minerals. Number 3, illite minerals shown in this figure, that is also the same pattern, one segment that have contained the silica sheet, alumina, silica, and thickness is same 10 angstrom, and same other segment of the part is silica, alumina, silica, total thickness 10 angstrom, and these two segments are joined together by potassium ions shown in this figure K plus. So, these are the three types of the minerals that is present in the clay minerals, clay soil that give provided the plasticity to the soil with addition of the some amount of the water present in that soil. Next is the topic is sieve analysis. What is sieve analysis? The process of separation of a given soil mass into different fraction by using a set of standard sieves is termed as sieve analysis. Sieves are made by weaving two set of spun brass and phosphor bronze stainless steel wires at right angles to one another. The square holes thus formed between the wires provide the limit which determine the size of the particles retained on a particular sieve. According to IS 1498-1970, the sieves are designed by the size of the square opening in mm or micron. 1 micron is equal to 0.001 mm. The diameter of sieve generally between 15 to 20 centimeters. The complete sieves divided into two parts. Number 1, coarse sieve analysis. Second, fine sieve analysis. Sieve analysis, the portion of the soil retained on 4.75 mm size sieve is termed as gravel fraction, and this fraction is used for a coarse sieve analysis. The set of sieves used for coarse sieve analysis are IS 80 mm, 40 mm, 20 mm, 10 mm and 4.75 mm sieves. The set of sieves used for fine sieve analysis are 2 mm, 1 mm, 600 micron, 425 micron, 212 micron, 150 micron and 75 microns. The sieves are stacked one over the other with decreasing size order from top to the bottom. A pan is the type of receiver which has no opening or holes at the bottom. It is used to receive the finest size particles from both coarse and fine sieve analysis for further identification. The selection of the required number, the selection of the required numbers of sieves is to obtain a good particle size distribution curve. So, this is the way to done the sieve analysis. We have to set up the sieves at the top, that is the larger size, and in the decreasing order to the bottom side. Last is provided the pan which receive the finest particle of the sample in the last. So, how we done this sieve analysis? This is the procedure. The following procedure is step by step adopted for performing dry sieve analysis. The oven dried sample of soil is taken in sufficient quantity as recommended in table below. So, this table that us provide the information about how much sample that have taken for this sieve analysis. So, in this table shown the maximum size of the particles in the soil sample. So, according to their maximum size of particles, the quantity that have taken for the sieve analysis as number 1 80 mm size, the quantity is 60 kg. Number 2 63 mm, the quantity taken 50 kg. Number 3 20 mm size particles, the quantity taken is 6.5 kg. Number 4 10 mm size particles, the quantity taken 1.5 kg, and 4.75 mm size particle, the quantity is 500 grams that are taken for the sieve analysis. Sieve analysis. The sample should not contain any lumps. It should be pulverized with wooden mallet. The sample is then sieved through 4.75 mm IS sieve. The portion retained on the sieve is taken for coarse sieve analysis, and the portion of the soil passing 4.75 mm IS sieve, that is taken for fine sieve analysis. The gravel fraction retained on 4.75 mm sieve is sieved through standard IS sieve as recommended for coarse analysis. Similarly, sand fraction passing 4.75 mm sieves, that is for fine analysis. The sample is then placed on the top sieve, and the set of sieve is kept on the mechanical sieve shaker machine, and the whole assembly is properly fitted with the clamp, and the machine is then started. The top of the sieve is also covered by the cover. The amount of mechanical depends upon the shape and the number of the particles. The weight of soil retained on each sieve and the pan is weighed. From the result, percentage passing through each sieve is calculated. So, shown this figure, that is the left hand side is the fine sieve analysis sieves, and right hand side is the coarser sieve analysis. Top is lid provided on the top of the sieve, and 2 mm, 1 mm, 600 micron, 425 micron, 212, 150 micron, 75 micron. Last is provided the pan. So, this is a set of fine sieve analysis, and as same as in the coarse sieve analysis is 80 mm, 40 mm, 20 mm, 10 mm, 4.75 mm, and last is pan provided. So, these are the sieve shakers set. So, it may be noted that combined sieve analysis, gravel fraction and sand fraction can also be carried out, selecting minimum number of sieves as per requirement of the sample. Next is the after sieve analysis. We know about the percentage of the passing material in each sieve and size of the sieve is also known, and then we have to plot the